let's start. All right, so to our third lecture, we are going to start looking at sorting algorithms. You may have seen some of the sorting algorithms before. We'll try to determine what makes a good sorting algorithm and what makes an algorithm bad. All right, so that's our plan of attack today. We already learned about recursion in the previous lecture, so that might be useful in some sorting algorithms. And again, I'll use Colab here. And let's see if I can actually, I probably have to sign in. That's a good point. I'll need to sign in as somebody. I don't know who I'll be. Yeah, I think this should do it. But then we'll have. I don't know which one. Nope. Yeah, that's going to be interesting if I get. Okay. Good. All right. So we'll look at the. Also, we'll start looking more into this big O notation, right? So the idea is, I hope we can see this, right? Yeah. Okay. Yeah. So we'll look at some of the searches again. Of course, again we'll recap the linear search and binary search from the first lecture, and then we'll look at some of the algorithms. Bubble sort, of course, infamous selection sort, insertion sort, merge sort, and we have time. We'll hopefully get today to the quick sort, which is it is quite well quick, right? But we'll see if it actually is better than merge sort, for example. Okay, right. So we will need to import some libraries since we'll be using Python. I'll connect to the virtual machine somewhere in Google servers. Let's see. And we will import some libraries. Again, so big O notation. One constant. So what's the idea of constant speed? If you say somebody says O1, basically.
It doesn't change. You can immediately.
Yeah, that's one thing is big immediately, but again, technically it could be maybe take million operations, but the idea is it doesn't change no matter you have one input or maybe 5 million items, right? It doesn't matter how many items you enter, basically you provide. So that's a big difference. So O1 does not necessarily mean it's instant. It's usually is, right? If you're using hash maps, for example, right? But O1 is usually a good thing. But you could make a really horrible O1 too, right? You could have a billion operations. It takes you 10 hours, right? No matter what you do, right? Sometimes academic literature, if you read academic research, you see this cool algorithm. It has this good performance, right? But it only works if you have like trillions of items, or even worse, like maybe something like 10 to the 60th items, which is basically not practical at all, right? Basically useless, right? But it's a cool algorithm, right? So yeah, things you can do lots of things in a constant time, right? You could set up things, right? Do some, I mean, do all kinds of weird things. But yeah, O1 generally is a good thing, right? Log n, of course, we saw in the big O notation, big O cheat sheet, right? A big O cheat sheet. This hope is still the same, but yeah, right? So you can see, of course, here, a number of elements, right? Log n looks close to O1 actually, on a pretty flat, flat with few elements, right? So log n grows slowly, right? If you have a million, log base 2 is how much going to be? Million items. Log base 2. Roughly. So 1,000. 1,000 is how much? Log base 2 of 1,000 is roughly how much?
8 or 10.
10. Because 10 roughly almost 10. Because 1024 is 2 to the 10th, right? So that's so million items you need 20 operations. Billion you need 30 roughly. I'm talking really roughly, right? So you can see how with very few operations you can do work on many items, right? On billion items, elements, right? So again, so log n is generally what we want, right? But of course, it's not always possible. Many algorithms, many tasks, many problems. You don't get log n no matter what you do. You'll see the search is one of those cases, right? Sorting. I mean, search is not one of those cases. Sorting will be one of those cases where log n is actually not possible, right? If you think about it, right? So so usually this is where we want to be. But when we get to like some graph algorithms, and turns out we can actually, best we can do is n squared or maybe n cubed, right? But again, keep in mind these are still, okay, well, n cubed, you have 1,000 items, 1,000 times 1,000 times 1,000, that's billion, right? So, still possible, maybe do some work. If you have 1,000 items, you have decent computer, possible it will work. If you have 10,000, then cubic is probably going to start getting really, really slow, right? So similarly, again, 2n is generally not really plausible. You know, like I said, you have 30 items, you only need billion operations, basically, right? So where does 2n appear, do you think? Do you know where does it appear? What kind of algorithms does it appear? Like, if you do full search, basically, if you look at all the possibilities, like you have this tree of variations, right? So this 2 to the n, right? If you start this, I go like this, right? Right. And here you have how many? Well, I don't know. You have you have 1, 2, 3, 4, right? That is maybe 3, but you have this tree of variations like 15 items already, right? 2 to the 4th basically already, you know, depth 4, right? 1, 2, 3, well 3 technically, right? But you only have 2 to the 4 items, you know, 15. I'm of course approximating this, but still, yeah. So, but again, so we'll look at search again, and this is a recap already, right? This is already a recap, so I'll go very quickly from the first lecture, right? If you define a linear search with a trivial algorithm, we'll look for the item, remember, right? And we return false or true, right? Return true if you find it, right?
Excuse me, can you zoom in a little?
Yes, I'll go bigger. Yeah, good. You have plenty of space. Is that better?
Yep.
Yeah. So we did this already in first lecture. Only difference here is we actually using a more efficient library, right? So we sort of shift the constant a little bit down because we're using NumPy. I remind you, NumPy is written in C, right? It's a low-level library. Actually, when we talk about data structures, we'll see that actually it's more basically it has better constant, has better speed than lists, the Python lists. But what's the downside? If you also used NumPy before, what's the downside with NumPy? You know, why shouldn't you use NumPy all the time as opposed to list? Any ideas? You use lists mostly in Python, right? That's your standard one. So NumPy is separate library. You import it, right? And it's much faster, right? But there's a downside. It's just basically a limitation because it requires only that your NumPy arrays have same number of items, same data types, meaning integers or floats or maybe strings, but they have to be same types, right? Lists, Python lists, they are sort of slow. Why? Because they let you have anything in them, right? You can throw whatever you want. True, false, floats, integers, strings, you put whatever on. All kinds of garbage you can put in a list, right? It doesn't complain, right? So because of this flexibility, it is also incurs some performance penalties actually, right? So there's no free lunch basically. That's what I'm saying.
But is it even a good programming practice to throw like many different types?
No, it's not. It's not. But Python doesn't yell at you, right? That's why Python is not. It's not. That's what I'm saying. Yeah. So, if possible, even if you're using lists, you should be using same data types. Meaning, right? Let's say integers, right? So sometimes, of course, integers and floats, you can sort of get away with that, right? Maybe, but still, with NumPy, there's no even for integers and floats, right? They have separate data types. So you have to choose, right? And that's how it works at hardware level if you think about it, right? This is actually more like data structures lecture already. That you have space in memory, right? If you have fixed size for each cell where you're going to store the data, right? That makes your computer work less, basically, right? You know exactly where everything goes, right? So if you have a list. List is basically actually a bunch of pointers, basically, right? List is a list, right? On an array, NP array, right? Array, all right? So this is basically, let's say, all integers, right? Let's say int, right? Let's say int 32, right? 4 bytes, right?
Yes.
Not 4 bytes, all 4 bytes. right? So this means we can have a contiguous amount of memory allocation. Is just, you know, whole bunch of block of memory, basically, right? Of course, there's paging, and if you want to go in details, it gets a little more complex, but still, you can see how this is more efficient, right? You just have this block a list. You can maybe, okay, int tarif2, maybe, right? And we don't, in Python, we don't see these types, you know, immediately. Maybe there's float. Okay, float could maybe take 4 bytes, but maybe it's 8 bytes, actually. Maybe it's a double, right? Maybe it's double, right? Maybe there's a string, and there's problem, what's a string? String might be maybe like a, you know, a declaration of independence, right? And it's maybe a long string, you know, maybe it's like a huge string, right? And the problem is, you know, like, I don't know, like maybe, you know, 10,000 bytes, 10k bytes, right? So you can see there's no really, you can't really store it, because especially in list, in Python, you can change the values, you can mutate the values, right? So you don't really have this, right? So this doesn't work. You have to have this, basically you have a pointers, right? List, right? You have int, so it goes to int somewhere, right? And you have somewhere maybe a float, right? Yeah, float 64, well, double 64, maybe a string somewhere, right? And so on, right? So this is much more efficient, right? And also because of modern CPU architecture, because of the caching, because also of prediction. Usually if you're going through some sort of memory, right? The CPU also tries to think for you. It's like, okay, if you are iterating over, it'll try to prefetch some things, actually. And so it means, like, until you get to the end, right, well, it'll already have the data, basically. It's like magic, of course, until it doesn't work, right? Until you hit, you know, you don't need it anymore. Of course, then, well, it discards this prediction, right? So this is how modern CPUs actually make some really efficient, you know, they're more efficient than it looks, basically. So arrays are amazing, actually. Again, we'll talk more about arrays in our data structures, right? So yeah, so but it all goes back. So we're going to be using NumPy arrays, which are basically C-type arrays. C++ type arrays, basically low-level arrays. And you see NumPy array. And I get L, I would say maybe R, maybe I would want to call it, actually, right? I should probably rename it here. Right, SKB type, LD type, I think it was, I forget now. Was it D type? Yeah, int64, right? So you see, so all members of NP array and the array, right, have to have the same data type. Unlike lists. So yeah, it's possible if you want to speed up your Python code and you have same data types, you should use NumPy arrays, definitely, right? So you get this low-level performance by using this high-level language. Okay, right. We'll do our back to linear search, right? And as we know, what's the problem with linear search? Of course, we're searching for 999, right? We have range, right? And again, I'm on this Google computer, so you'll see 30 milliseconds, right? Because it had to go to the end. We already talked about this, right? And we look for the beginning, right? It means we will get it very quickly, 600 nanoseconds. Not bad, right? So big difference, right? Whether first or last, right? If I search for something non-existing, interestingly enough, it looks like here it was a much longer time to search. I wonder why is that the case? Because 999 is the last, right? And that might be actually because I'm looking for this large number, actually, right? Well, no, it's about the same, actually, so everything's cool, right? Actually, sometimes you see these previous cells, it could be because they were run on a computer running on the batteries, right? And sometimes if it goes into low performance mode, right, the speed drops, actually, right? So sometimes you're getting weird results. Check if your laptop is running on like a low battery and it's gone. The speed actually has decreased. Actually, right? It's one way of telling. Actually, right? So if it goes under 20% or maybe under 10%, there's a performance setting, right, in power mode, right? So you need to check that, right? So yeah. So this looks all normal, right? And we see again. I'll do one more check. And of course, if you think about it, I was searching for this item, right? This number, big number. And I get 999. 999 is the last, right? So 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 it really can't really exist in this particular data set, right? Because oh no, it can. So it can in 64. Okay, so it probably can, because I guess it does fit. It's like 53 billion, right? Yeah, that's no problem, right? But yeah, if I was doing int 32, right, and it's sine, right, upper limit would be only about 2 billion. Sine, unsigned would be 4 billion, right? Because 2 to the 32 is about 4 billion something, right? Okay, so. Right, so you see this big difference, right? So hypothesis. There's hypothesis that looking for big number is there's a penalty, slight penalty, but it doesn't seem like too much penalty here. Plus minus, yeah, it doesn't look like there's much of a penalty, right? Time scales linearly. That's our main takeaway, of course. So n items, if you had more items, the longer it takes, right? So binary search. Again, let's go back to our binary search, which is basically, if you have a way of using binary search in your problem, right, you should, right? So always look for a way of dividing your problem in smaller areas, basically, right? So binary search iterative, right? Iterative, what does iterative means? Iterative.
It iterates through it.
Yeah, iterates through. Loop-based meaning. We're not going to use. It's not recursive. In this here, it means it's to separate from the recursive solution, right? So A and T, array on T would be the needle, right? The needle here, right? I probably should write this. Oh, because I'm using the wrong. This is an old notebook. That happens. You see? No, this looks okay. No, it's fine. No, this is good. No, this is fine. Yeah. But I want to test what happens. Your old code, you write, you want to rewrite it, right? Because no matter how confident you feel in your skills, 6 months later you'll see what kind of idiot wrote this code, right? So that happens, right? So if you could look back to your code you wrote 6 months ago, you'll see. So yeah, but of course, binary search iterative. What's the idea? We have our length, right? We have our upper index. Right, the last index, right? Now this is the start index, right? Start index, and we keep dividing our search space. Again, remember, we're using the Pythonic, the integer division, right? We looked at this algorithm, right? Again, if I woke you up this in the middle of the night and made you do this, by hand, sort of write this like on a blackboard, it's easy to miss this middle part, right? This making off by one error, right? Because you have the indexing, right? But so when you're writing something like this, of course, hopefully your language provides already a binary search, right? For this actually, turns out Python does actually. Python does offer binary search built in actually. But sometimes you don't have a binary search. You can't use something out of the box. If you can. One of the takeaways should be, if you have a library which does this, in practice, of course, you should be using it, right? We are here in the classroom setting, but if you're in production, if you are at work or doing a project, right, which, if it's allowed, if the teacher said, don't use built-in libraries, maybe, sometimes teachers are like that, right? But in general, you should be using the built-in libraries, right? If there's binary search built in your language, right, use it, right? So, okay, because it's easy to make a mistake. Right, so while lower less or equal to upper, because okay, you can make a mistake by maybe not comparing here, for example, right? Less or equal, right? Things like that, middle, lower plus upper, right? So if it's middle, you return true, right? And again, this only works, of course, when it's sorted, right? Again, if we have random numbers, obviously it's not going to work, right? You can get maybe very lucky, right? Maybe get very lucky. But most likely you'll miss it, right? You have just a bunch of uncertain numbers. You probably, by doing this binary search, the binary search will work, but most likely you'll get a false answer because you'll miss, the sort. There's no sorting, so all of this fancy lower upper is not going to do anything, right? So is everybody clear on this binary search how it works? Okay. All right. So I'll do it again. Range. Of course, I need to actually have the function working. And again, we'll see this now. will be much, much quicker. So 9 microseconds, right? And we had how many microseconds? Milliseconds. So yeah, so it's not nanoseconds, obviously, because with nanoseconds you have the first item, right? You just get out of bed, right? Heat up the, turn on the CPU, basically, right? Look for memory access, basically, and you get the first item, when you finish, right? But microsecond, that's good, right? That's good. So iterative, and it should be. The only thing is, it should be a little bit slower, right? A little bit slower. And there actually was recently on Hacker News, which is a website for basically, for startups, all kinds of programming and coding and business things. There was talk of Steve Ballmer. Do you know who Steve Ballmer is?
No.
Who can tell me who Steve Ballmer is? He has two. Well, he's famous for two things, right? Nobody knows who Steve Ballmer is. No. He's
CEO of Microsoft.
Yes, he's currently the largest stockholder. Yes.
Yeah, Google, I don't know.
Yeah. So he's currently the largest stockholder of Microsoft stock because he was smart. Well, he was not as charitable. Let's say this way. Bill Gates gave away a lot of his stock to charity. Basically, well, he still controls it, but for Africa and all that good stuff, right? Paul Allen, second in command for Microsoft. He died maybe a couple of years ago, but Steve Ballmer, right? He's still alive. He's also famous for what? Well, these days, what does he do these days? You can probably read up. What does he do? Besides Microsoft stock, owning lots of stock. What does he do? Los Angeles. He's pretty famous as being very active in, you guys don't follow NBA. LA Clippers, Los Angeles Clippers. He owns Los Angeles Clippers. And he's famous since he's worth about 160 billion at the current stock price, right? He has more money than all the other NBA team owners combined. And those guys are not poor, right? They are billionaires, right? He has more money than them all together, basically, right? So he basically could, outspend them all, right? So he's famous for bringing out LA Clippers from being a really bad team and really bad owners, really stingy owners. He spends money, right? So he's also famous for jumping, in the NBA. So if you follow NBA, you would see clips of him, right? He's pretty much, he looks like, he looks like somebody who does drugs, but he probably doesn't do drugs. He's just naturally like that, right? Yes. He's naturally super hyperactive, basically, right? I don't know what he puts in his coffee. I don't know. It's funny, right? But let's go back to the story about Steve Ballmer and binary search. Okay, so I'll do a Google search, Steve Ballmer, binary search. Let's see if my Google, yeah. But basically, yeah, Steve Ballmer was wrong. This is like recently, but yeah. I wouldn't say, of course, this is kind of clickbait, of course, right? You always write blog posts saying somebody was wrong and then somebody is correct. You know you were wrong, right? So yeah, but basic idea is this, right? So this is job interview, right? You go to Microsoft like maybe 10 years ago, right? And he would write to give you, relatively high level, right? And he gives you this question, right? 1 to 10, right? And he asks you this, high, low, right? Like binary search, right? It smells like binary search. He'll give you $5 for if you get on the first guess, $4 for second guess, $3 for third, second. So let's do this math. 5, 4, 3, 2, 1, 0. That's 1, 2, 3, 4. It's like six tries, right? On 6th try you get nothing. On 7th try you pay $1. On 8th try you pay him $2. Now, on 9th try you pay 3, I guess, right? So the question is, should you play his game, right? Right, and that's a kind of, so the question, was he wrong or not? So what's the idea, right? The thing is, he's considered like, he wants to trick you basically a little bit, right? So you should play his game. Idea is this, if you do a regular binary search, right, how many tries do you need? Well, what's the worst case scenario?
100.
Well, okay, let's do the math. It's 1 to 100. So you have 100 items, right? So how many? Remember what I mentioned, the mathematical operation. What operation do we need to figure out this?
Log 2 of them.
Yes, exactly. So, yeah, this is 100,000, right? Yeah, here you see this actually, right? So I'll do a little aside, I'll add a little text here. Was Steve Ballmer wrong? Usually, if a blog post asks a question, the answer is no, right? Oldest rule, one of those. Somebody, if you see a news article that was somebody, you know, if it's a question, it's probably the answer is no, right? So, but yeah, so I'll give a link, right? But yeah, so let's do this code. So base log. So math, they need import, right? Import math.
It'll be 6 point something.
Yeah, 6 exactly. Math log 100 should be 6 point something, right? Or log 2, sorry. That's base 2, I think. That's base E. That's base E. Sorry, that's base E. Yeah, yeah, 6.6. So this, what does this mean?
This means that you might use up all of your 6 tries.
Yes. So yeah, you have to be very careful with this Steve Ballmer guy, right? He didn't get $160 billion for nothing, right? So, right? So maybe he wants to take your last dollar, right? So, yeah. So this means if you are really unlucky, right? You might need 7 tries. So so worst case scenario, you should lose $1 unless unless you really, I don't know, unless you do linear search, right? Then you owe him like $90 maybe, right? Right. So now, so technically, yeah. So 7. So the question is now, what's the idea? It's Steve Ballmer's idea. Why maybe this guy is arguing he's wrong. The idea was that Steve Ballmer now, okay, he's going to use binary search. I'll make it sure to choose a number, one of those numbers, which takes 7 tries, right? So this could be like number like 1, I believe. No, let's see, number 1, yeah. Yeah, because you keep in half. Yeah, 1 would be one of those numbers, like somewhere in the middle also. Like not 50, right? Because 50 you hit on the first try. You make $5, right? If you hit 50. So what was the idea? This guy in the blog post, you'll see this blog, I'll update this code after the break. What is the idea? Idea was that you don't necessarily need to pick 50 as a middle, right? What's the idea? You have 100, you don't need, if you're picking from 1 to 100 and you have 7 tries, right? What you can do is actually minimize, you can do a little random things, like maybe choose 49, sometimes 51, right? Sort of trick, go back at the Steve Ballmer guy and sort of trick him, right? He doesn't know what's your middle going to be, right? So you have a little bit of freedom, right? That's the idea of this guy. So technically, right, mathematically this guy demonstrates you're winning about $20 on average, right? Right. So it's positive, right? Yeah. Yeah. So idea is there. So all those 100 numbers, there are 37 that will require you to ask 6 questions, right? So, but that is if Ballmer is a very good strategy, right? If you have fixed numbers, right? So you counter by doing some randomness. So yeah, one of the big research areas in modern algorithm theory is this probabilistic algorithms, meaning you don't do everything exactly the same way. So this is like a really simple example of how you can do some variations, some tiny variations in the algorithms, right? On you get better performance actually. Well, what you want actually is maybe not better performance, but you avoid outliers, right? Outliers are bad, right? Because adversary, right? Maybe a hacker, maybe attacker, right? They know what kind of search algorithm you're using, or what kind of, and they figure, okay, I'll supply these numbers, and now they will lead to this worst case performance. Because oftentimes you want to know, is there like really bad, evil cases, basically, right? The adversarial cases where your algorithm is really slow, right? And also, how likely is that going to happen? Is it easy to do this or no, right? If it's like just extremely unlikely, right, and it's basically impossible to do this type of attack, then okay. But you can counter it often with adding a little bit of randomness. So that's something to keep in for future your tool set, right? If sometimes it's seems like it's one way of fixing things is actually doing a little randomness. So key takeaway from this article, one of the takeaway from the article is that a bit of randomness can counter an adversary. Right. All right. Okay. Now let's go back. So yeah. So O1 middle, O log n is average. Worst log n. Right. in this case, well, in this case, log n also was considered the worst case of log n, right? Okay, so let's go back and recap before the break. Let's look at the binary search recursive, right? So upper, lower, right? And this is actually a bit tricky, but basically same idea, except instead of supplying the index, we are supplying a new or a subset, a slice of the array, right? That's the same thing. And it's a little bit tricky sometimes to do a recursive one actually here, because you are supplying a subarray, and is it actually a copy, or is it the same array? Hopefully it's the same array, right? Because otherwise it takes time to move memory, right? To move a bunch of memory around. So that's basically, copying out of place, but you probably don't want that. Let's take a look. Oh, is it faster? It should be probably same speed. Okay, 16 microseconds, not too bad, right? And if you look for, maybe if you look for a fake number, like not fake, but a big number, yeah. Yeah. So so even non-existent numbers, Okay, by the way, yeah. So there's bisect, which is basic binary search, right? So obviously it will not work if it is not sorted, obviously. So use bisect, right? You don't have to worry about it, right? And again, let's see, return index, right? Where this item should be, right? So I should put this note here so I remember. Use this in production. Yeah. Production. Real life. Use built-in library or other good libraries if possible, right? Yeah. All right. Now, so this leads to sorting algorithms, to actual main theme today, right? And the next lecture, this week's next lecture as well, right? So I want to think of the worst algorithm, my favorite worst algorithm, and it's actually I call this Bogosort. It has its own Wikipedia page. What's the idea? Idea is this: you throw your items, your cards or elements up, you let them randomly land, and you check if it's sorted, right?
Yeah.
Yeah. The hilarious thing, is that it actually works. It actually works, right? It's a probabilistic algorithm, right? It's a so I'm gonna, since I don't want to do randomness myself, right? Shuffling is hard to get right correctly, by the way. There's some interview questions where shuffling is asked. For shuffling is its own section on how to do shuffle, right? So for now, I'll import it from the library. And here's a fantastically simple algorithm. So is sorted. How do you determine if something is sorted, right? Well, you check whether each pair, whether the first one is less or equal than the second, right? You have to go through all the pairs, right? No other way around it, right? Maybe you can do some variations, but you have to check all the, you have to go through. It's a linear, right? It's a linear, so that's why also kind of, no matter how good your algorithms, right, for sorting, at some point you have to determine if it is sorted, right? So you do need this linear path, right? So all sorting algorithms, by the fact that you need to determine if it's sorted, right, you have this lower bound of linear on, right? That's the lower, right? But we'll see what's there's no, sky is the limit in complexity, right? You can make a really bad algorithm like this one here. We'll start with the worst algorithm. So all data we check, this is linear check, right? All data, right? Universal quantor, right? Check true, right? It's instead of, I could do a loop, right? But I use Python language, so this hides a loop. This is a loop, right? There's an iterator here, right? Yeah. So that's the thing with Python and another language too, right? Modern high-level languages, there might be a loop hidden, like in this case here, right? Because you have to check all these pairs, right? And then you turn true, 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 true. If all of them are true, this is true. If one of them is false, if there's one drop of oil in a honey jar, right, it's going to be false, right? One of these is false, it's all false, right? Okay, so that's is sorted, but the Bogosort itself is really simple. Look at this, I love this algorithm, right? While it's not sorted, shuffle, return data, right? Super, right? So simple does not mean fast, right?
But it could be fast.
Yeah.
It could be fast.
The
So
most efficient algorithm.
yes. So let's try this. I have 5 items, right? My data, some items on my Bogo data. It's fast. Yeah, I sorted. It's sorted, right? It works.
Yeah.
So for 5 items, it works, right? So let's do more. So yeah, so my data. So one thing, another thing is mentioned. This is in place, right? The shuffling, this part here, right? Another thing you have to pay attention when you're looking at sorting algorithms, right? In place, right? I don't know if in your Python lessons you talked about this in place, out of place. Many operations, they have distinction in place or out of place. What's the difference? This term. You'll encounter it in other languages too, program language. In place means you modify the data, right? Because notice, I do shuffle on the data, means this data is going to be modified, right? But out of place means you return some new data. When you're doing functional programming, oftentimes you can't even modify. In functional programming style, you can't modify, you're not allowed to modify the original. You return the new data all the time, right? Again, it's kind of, you avoid some bugs, but it's kind of, can get also expensive. Because if you have this huge array of data, right? Just imagine you have to get a new one each time, right? It means you have to copy memory. It's expensive. Oftentimes, if you do not need the original, right? Remember, we are destroying the original, right? Here, original is destroyed, right? I don't know the original order, right? It's gone, right? I didn't copy it, right? So let's time it. So 5 data, and again, well, so my data, it's going to be really hard to actually time it. Why? Because it's already sorted, right? So basically, I'm getting linear sort here, right? 1.39 microseconds, right? Very good. Well, because I didn't have to do it. So I need to reset and write. So I can do this reset, but it's unfortunately, but is it enough? But is it enough? We're gonna do a break in like 1 minute. We'll finish this, right? So it's still gonna be a little bit slower because the first operation is gonna be sorting, right? Afterwards, it will hit this. You see, 1.3 minus. It's actually still. We didn't really gain any. We kept the same speed, right? So also we maybe got really lucky. Yeah. Okay. But now let's do this. So again, what is random seed? I mentioned this before.
To make the same number.
Yeah. So they look like random, but they're not really random, basically, right? So random, it could be any number, 2024, whatever, right? And of course, the small data. 42 is from the Hitchhiker's Guide to the Galaxy, the book. But it could be any number. Small data, I'm going to do numbers from 0. Okay, so round integer method. Right, unfortunately, Google Cloud is not giving me good, but it's basically 0 to 100, 10 items, right? So I have my data. It should be same as before, right? Okay. So it has some doubles. That's fine. And now I'm going to sort it, right? I'm going to sort it, right? And again, this is not efficient because I mean it's not representative because the first time it has to do all this work. Afterwards, it's already sorted, right? So you see, it's okay. So it's sorted, right? Right? It is so. Yeah, it is sorted, of course, right? Why didn't I? It's a single timing. Oh yeah, it's nice. So it took 9 seconds. Okay, sure. Yeah. So notice. Yeah. So this one single. This is a single run, right? So now it's going to be very fast. It should be very fast. So this is 9 seconds the first time, right? And now it's 3 microseconds. But it's already sorted. We didn't have to do anything, right? So. No, so this is it's actually, we do not need any randomness, right? Okay, so this means we had, a couple million times, right? So the question is how many times do we have on average to see if we have it sorted, right? So this would require using some combinatorics. I think about So factorial something, 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 right?
Yeah.
Yeah. So we'll do that after the break, right? So hopefully you can see the idea of how this random algorithm works, right? And also hopefully you can see this is not so good, right, for large items. I don't think we can sort 100 items with this. We have to be extremely lucky.
But we can try still.
Yeah, we can try, but then we probably don't need to, we can leave the computer running for the whole semester, right? Have the computer set up in the back. Maybe it will sort, right? But I think we'll have better odds of, mining Bitcoin these days or hitting lottery, right? So, yeah.
They're insane.
Yeah.
What makes me.
To pirmo calculator.
Yeah.
Jā, tur bija tas...
Bet tev nav gambling mindset, saproti.
Zaudētāju maiņas.